In this lab, I wish to further explore constant velocity motion through visual observations and computational models. To visually track the motion of our object, we use Tracker. After collecting the observed data, we built a computational model using VPython on CloseScript. Throughout this exploration, we discovered that constant velocity motion caused the objects to change its position in fixed intervals over time. Before analyzing our data, one must become cognizant of a few physics concepts. We begin by defining our terms. Displacement is a vector quantity that signifies the change in an object's position according to a reference point. Velocity is a vector quantity that signifies the change in displacement over a time span. Acceleration is the change in velocity, and a force is a push or pull that can change the motion of an object. Newton's first law, or the law of inertia, states that an object in motion stays in motion unless acted upon by an external force. Similarly, it stays at rest unless acted upon by an external force. Newton's second law allows us to quantify the direct relationship between force and acceleration through the equation force equals mass times acceleration. With force having the units of Newton, we begin to dissect our experiment. In this experiment, our setup involved a tennis ball, and our system was a tennis ball, and its surroundings included the Earth and the kitchen island. Our initial conditions involved us setting the tennis ball on a kitchen island and placing a camera at a certain point of reference. After pushing the ball, we allowed the ball to reach constant velocity and began our analysis from there. As you can see, this was our overall setup. We chose to study our data of the tennis ball by rolling it on a kitchen island. As shown in our observed data, the constant velocity led the object to change its position by a discrete amount over time intervals. In this experiment, we chose to monitor data over every 0.033 seconds. Other than the discrepancy we observe at 0.45 seconds, our data followed a clear linear trend. To build our computational model, we changed the starter code to incorporate the mass of a standard tennis ball in kilograms and set its velocity by calculating the average velocity through the division of the total change in displacement over time. After setting the initial values, we set up a while loop to calculate and update our values through each iteration. By setting the net force to 0 and using the Newton's second law to update the ball's velocity and position every delta t seconds, we were able to program our model to predict the object's motion over a certain time span. As shown by the graph, our model was pretty efficient at predicting the motion of our object. Disregarding our outlier here, our model was pretty efficient, but the only problem with our model was the initial position. Despite updating the initial position in our code to be at the origin, some human error led the model to predict a different initial position. If I were to flip the orientation of my axes, however, then the graph shown above would have been reflected over the y-axis. In other words, our object would have started at the origin and proceeded to move in the negative direction. Keep in mind, the negative term is in quotation because we still choose to keep our point of reference the same and just flip the axes. Similarly, the velocity would have been different due to the change in direction. Even though our reference point was still the same, the axes were flipped, causing the change in direction to be in a completely different direction. And since velocity is a vector quantity, it was different. However, even though the graph was negative, the slope would have been the same since the speed or the magnitude of our velocity would have been the same. In a sense, I think it is possible to calculate the number of forces that added up to get the net force of 0. In this experiment, we chose to ignore friction. However, by arbitrarily determining our system and its surroundings, we can calculate that the force at play are as follows. Initially, the forces include the push force with our hand, the normal force acted upon by the island, and the gravitational force acted upon by the Earth. And after a certain point, when the object has reached constant motion, the only forces acting upon the object are the normal force and the gravitational force. I would like to say, however, if we altered our assumptions, like including friction, the forces that would come into play would include friction and drag. Thank you.